6, and my team members are Saiket Ghosh, myself Abhishek Chipa, Sandeep Kumar, and Saurav Chaudhary. So these are the table of contents that we are covering in this our LMI project group. So I will start initially with quantization of light. Then I will cover a bit part of single mode quantization. Then my friend Sandeep will go further it, and my other team members will explain the multimode quantization. So let's start with the introduction part, that is quantization of light. What you mean by quantization? Meaning, if you are cutting all the continuous frame in small partition, this is what called quantization. So what does it mean by quantized light? In quantum mechanics, we simply assume that our electromagnetic radiation is a wave, right? So classically, electromagnetism is considered it's as a continuous wave. But in quantum mechanics, we consider it in a chunks of energy packets that is called photons. So what is the classical view of light? In classical physics, light is described as a continuous electromagnetic wave as per Maxwell's equation. And what are the limitations of classical theory? So basically, what is the idea of assuming that we, electromagnetic waves follow a quantization? So the idea is, because from continuous wave propagation, we can't explain the photoelectric effect. So these are the some restriction or limitation of classical theory. So that's why we impose quantum mechanics in our explaining photoelectric effect. Let's see quantum perspective. So in quantum mechanics, the electromagnetic field is quantized. This means energy is not continuous, but it exists in discrete packets of chunks, which is called photons. So each photon carries energy given by Planck relation. And what is the Planck relation? E equals to h nu, where nu is the frequency of light. And what is h? H is a Planck constant. Very good. So far, so good. So what is the motivation of quantization? So quantization explains why only light above a certain frequency can eject electron. Like we know the photoelectric effect. So these are the some questions that require the quantum nature of light. And in explaining the multimode quantization, we start with the analogy of harmonic oscillator. So each mode of electromagnetic field behave like a quantum harmonic oscillator, and it has a discrete energy levels. We all know that. So sorry. So why start with the single mode field? These are the some questions. So how we will proceed in explaining multimode. So we start with the single mode. Why we are doing with single mode? Because initially we want to start with the simplest case. So if we assume that our radiation wave has only one frequency, in that case, our frequency radiation is single mode. So this simplifies our problem and builds a physical intuition. So what is the role of cavity? So we will impose a cavity here. And what will be the cavity? The conducting plates. Two conducting plates will be there. It in a more broad way in couple of minutes. Second thing is motivation. So what is the motivation of doing this quantization of light? So first thing is it it helps in deeper understanding of superposition, entanglement, and decoherence in realistic quantum system. Second thing is new approach. It open up the new approaches to scalable and reconfiguration quantum networks by coupling modes through nonlinear optics. Third thing is a framework. It design a framework for describing quantum fluctuation that underlies noise, sensitivity, and measurement precision in quantum system. And fourth thing, a unified platform to explore various degree of freedom, spatial, spectral, temporal, and polarization. So these are some key motivation for us doing these things. And where it helps us, it helps in quantum computing, secure communication, you know about quantum cryptography, and quantum sensing and fundamental test of quantum mechanics. Okay, so this is the broad idea of why we are doing this and what is our motivation. So let's start with some mathematical tools and terms that will help us in understanding multimode quantization of light. So let's start with the quantization field. So quantization of single mode field. What you mean by single mode? It means we are dealing with only one frequency, one polarization. Okay, so we began with the case of radiation field confined to a one-dimensional cavity. So this side and this side we are placing two conducting plates, and this direction is a z, which is the propagation of wave. So by imposing the cavity, what happens? It happens that the wave, this radiation is becomes standing. So it get trapped in this conducting plates. So the electric field must vanish on boundary condition. So there is a reason of choosing conducting plates. What is the reason? Because any conductor, it has some boundary condition for electromagnetic waves. What are the boundary condition? That E parallel is 0 and B perpendicular is 0 on the surface of the plate. So these are some crucial boundary conditions that helps us in trapping the electromagnetic radiation. So we assume there are no source of radiation. This is one crucial point, and no currents or charge, neither a dielectric medium in this cavity. Correct? So the medium, the field is assumed to be polarized along the x direction. So we can write simply ext equals to exzt, where this small ex is the polarization direction. And we will use Maxwell equation. So we have four Maxwell equation: del cross E equals to minus del V by del T, del cross B equals to mu naught epsilon naught del E by del T, and del dot B equals to 0 and del dot E equals to 0. Okay, by using these Maxwell four equation, we will get a wave equation, which will helps us in deriving this expression, which is Ex equals to 2 omega square V epsilon naught square root Qt sine kz. Correct? So where omega is the frequency of the mode and k is the wave vector related to the frequency according omega is equal to ck. So this relation is very important. We have to remember it. Okay. So what are the boundary condition? Boundary condition are simply that electric field parallel has to be diminished at the boundary. And what is the boundary? Z equals to 0 and Z equals to L. Correct? So we assume that omega in equation 2.5, this is our equation number 2.5, is one of this frequency and ignore the rest of them. Correct? And V is what? V is our effective volume of cavity. So Qt is the time dependent factor having the dimension of length. And by getting this Ex, we can also get the By component. And how will we get a By component? By equation 2.2. So with the help of equation 2.2, we can get the By, magnetic field component. So here we get Byzt equals to mu 0 upon epsilon naught square root 2 omega square V epsilon naught square root Q dot T cos kz, where Q dot T, we define it as P of T, same as we do in classical mechanics. We define momentum and position operator. So canonical momentum and canonical position. So the classical field energy H is defined as energy of electric field and magnetic field. The combined form is known as classical field energy. So H equals to half epsilon naught Ex square plus d square upon my mu naught integrating dV. Why we are integrating with dV? Because H is our total energy. Correct. So I get the expression, the straightforward expression H equals to half Q square plus omega square Q square. We simply absorb the M component. So you can see this expression is same as classical harmonic oscillator. Correct. And in quantum mechanics, we simply in classical harmonic oscillator to going to quantum harmonic oscillator, we simply change the momentum and position things into operator form. And these operator follows commutation relation. And what is the commutation relation? Commutation bracket QP equals to iota H cut. So with the help of this conversion from classical to quantum, we can simply write our electric and magnetic field operator in this form that you can see in equation 2.10 and 2.11. So now finally we obtain the quantized Hamiltonian, that is H operator equals to half P cap square plus omega square Q cap square. And to deal with in a simplest manner, what we can do? We can simply do conversion to creation and annihilation operator. So we define, to keep our calculation a bit simpler, we simply define A and A dagger. These are our creation and annihilation operator. Correct. So by using these 2.13 and 2.14 and by massaging these two equations, we can convert Q and P in this creation and annihilation operator. So these are the expression of creation and annihilation operator in the form of Q and P operator. So our magnetic and electric operator becomes simply Ex equals to E0 A plus A dagger sin kz, and By becomes B0 A minus A dagger cos kz, where E0 is simply h cat omega upon epsilon naught V square root, and B0 is mu 0 upon k epsilon h omega cube by V square root. So these represent the field amplitude per photons. Correct. So the operator A and dagger, these are some extra things that you have to remember, which are the operator A and A dagger follows some condition A dagger equals to 1. So our Hamiltonian become H equals to h cut omega A dagger A plus half, where we can also define A dagger A equals to an operator, that is number operator. Evolution in Heisenberg picture, we can simply write d by dt of any operator can be written as I by h cut commutation h o, and by applying this thing for getting the time evolution of creation or annihilation operator, we get the expression of time dependent annihilation operator equals to a e की power minus iota omega t, and for the creation operator the time dependency would be simply a dagger equals to a dagger 0 e की power iota omega t. And this is what I already told you, that n is defined as number operator, that is a dagger a. Okay, so this is the simple mechanism or things that this or Hamiltonian will follow. So we can get the final energy levels En equals to h cut omega n plus half, where n is the number and n cap is a number operator. So if I define or draw in a diagram that how these energy levels differs, you can see this in this diagram. So our lowest energy is at what? N equals to 0. So n equals to 0 is 0.5 h cut omega. Okay, then if I put n equals to 1, energy would be 1. The difference of two consecutive energies is 1 h cut omega. So this is what we got in this quantum harmonic oscillator thing. Okay, so now let's jump in.
Hello, my name is Sandeep, and in this section, we will focus on quantum fluctuation of a single mode field. So we know what is the number state. The number state is a well-defined energy or a photon, you can say, where the phase is always remain uncertain. So suppose you have a n equals to 3, so your photon number, meaning 3 is a 3 is well-defined photon number, and you have uncertainty in your phase. So here in this equation, we can see that the here in this equation, the expectation value of the electric field operator in number state equals to the E naught times sine of kz uh, multiply with expectation value of annihilation and creation operators, and which is equals to 0. So the mean is 0. It doesn't mean that your fluctuation is 0. So if you square this electric field vector operator, then we will find that there is a n term in this equation here. It is expressed as the expectation value of the square of the electric field vector is equals to E naught square times the sine square kz, which is further multiplied with the annihilation expectation value of the annihilation square plus the creation of square plus summation of the product of the these uh, two operators where the n terms comes. So this depends on n. So as you increase the n, uh, your fluctuation will increase. So there is a fluctuation, meaning we can define it, we can characterize it in terms of variance. So variance can be expressed in this form, where you have the variation of electric field operator equals to the square of the electric field vector minus the average of this square. And you can also derive the standard derivation, which is a root square of root of variation. So now the number state are taken here to represent the state of the field containing n photons that we know, and we have not specifically derived anything here. So in accordance with the uncertainty principle, the number operator does not commute with the electric field operator. There is a relation between them, which is equals to E naught times sine of kz multiplied with the difference of creation operator minus annihilation operator. So there is a complementary relation between these two, and so for the number set m, the right hand side vanishes completely, but there is an uncertainty always available here. So there is a connection here to the notion of the phase of the electric field. In as we know, the classical physics, amplitude and the phase of the field can be simultaneously defined, but this is not the case in the quantum mechanics. Uh, so in fact, in the history, the concept of quantum phase operator is long and continuous, and we shall have deal with this issue at length later. For now, we simply take this point for which the phase is in some sense complementary to a number. So if we recall the time and energy relation of uncertainty of Heisenberg, then we will definitely see here the phase uncertainty between the number and the phase with the same analogy. So from this, we can argue that the well-defined phase, the photon number is uncertain, whereas a well-defined photon number has the uncertainty in their uh, phase. So coming to the quadrature operator, so from the equation 2.15, uh, here we have derived the electric field operator in terms of a creation and annihilation operator. Uh, now, if we back to the now, if we also include the time independence, a time dependence of this field, then this equation becomes equals to E naught times annihilation operator times e to the power minus I omega t plus creation operator times e to the power I omega t sine kz, where this minus I omega e to the power minus I omega t, it is the wave traveling with the omega frequency of omega, and these both are out of phase, meaning if it is traveling in one direction, then this other direction. And this sine kz is the wave propagation. So we now introduce the quadrature operators, which is x1 and x2, which is derived here. So these quadrature operators, are out of phase with each other. And here this term 1 by 2i in this x2, meaning it is a imaginary part of the wave. So if we include the x1, x2 uh, in this electric field, then we will get this expression 2 times e to the power sine of kz, x1 cos omega t and x2 sine omega t, where x1 and x2 both are out of phase with a 90-degree. And this x1 corresponds to cos omega t, and sine x2 corresponds to sine omega t. And you can relate this x1 and x2 as a position and momentum operators of, and they follow the commutation relation as this. So x1 and x2, which gives you the relation between both of them. So it is I by 2, so it is not 0, meaning there is a uncertainty and in their relation. So the uncertainty is given by this expression, uncertainty in the quadrature 1 multiplied with uncertainty with quadrature 2, which is always greater than or equal to 1 by 4. And if we find this expectation value of this quadrature 1 uh, with a photon number n is always equals to 0. But if we take the square of these operators, then the uncertainty is always there. The expectation value will be 4, 1 by 4, which is equal to which is equal for x2 also. And there is again the relation of n comes here. So what if we make n equals to 0, meaning in the vacuum state? So this will be 1 by 4. So in the vacuum state, which is always the minimum state, so the vacuum state is always the minimum uncertainty state here. So x1 and x2 is always 1 by 4. So now the multimode will be discussed by Saurav.
Okay, so hello everyone. My name is Saurav Chaudhary, and I will be explaining multimode fields from here. So, as the results from a single mode cases, we can extend this to multimode radiations. So, meaning that multimode oscillations, we assume some criteria here. So, the field will be exist in a free space. So, what it means, it actually means that where we are field exist, there will be no charge or no current. So the Maxwell equations will be valid here. So this condition actually ensures that the field is behave as a pure radiation without any external influence. So we will move forward for the mathematical formulations for the multimode fields. So for the description of a multimode field, we will use a vector potential, ART, where R is a position and T is defined as a time. So which will be satisfied the wave equation. So the wave equation we can see here is 2.55. So now this equation actually describes how the vector potential is propagating in a free space. So for the classical wave equation, the electromagnetic wave start at the second special derivation. And here you can see that the second derivative is 1 by c square, where c is the speed of light, as we will know. So additionally, the Coulomb condition is imposed. The Coulomb condition is specifically choice of gauge. So the gauge the gauge electromagnetic choice, we simplifies the Maxwell equation, imposing the constraint on the vector potential. So the main benefit of using gauge condition is that it eliminates the unnecessary degrees of freedom from the vector potential. So we can actually manage the vector potential more efficiently. So we will be now uh, like giving expressions for the electric and magnetic fields from the vector potential. So the electric field is given by ERT equals to minus del A RT by del T. Here the minus is showing us the Faraday law is valid here. So the electric field actually opposes the change in a magnetic field. So we all know that about this. So we will be like seeing this magnetic field. The magnetic field is given by the del cross of vector potential, which means that the magnetic field is given by the curl of vector potential. These relations from directly from Maxwell equation are common in classical electromagnetism. So we will be like here assuming a large space cavity to actually make sure the more manageable calculations. So we will be choosing cubic cavity for the side length of L, which actually has the perfect wall reflecting walls, the same as we have seen in a single mode. So the reason behind this assumption is we can see here the cavity is chosen to be large compared to any sitting inside, like atom or anything. The cavity is much more larger than the wave function, the wavelength of a electromagnetic field. So the model should remain valid even if we take the length L to infinite. This approach is actually very common in physics. So imposing boundary condition in a finite system, which actually help us to analyze the essentials of the physics. So we will be now imposing the boundary condition. So the description to allowed field modes, actually the periodic boundary condition are applied here in the x direction of a plane wave solution, which we can see here the e raised to ix x equals to e raised to ix x plus l, which means that the position or wave function actually will be the same at x or x plus l. So it ensures that it repeating some pattern. From this condition, we can derive the allowed values from wave vector x. So here we are taking for a x direction, the kx equals to 2 pi upon L mx, and the mx values are can be 0, plus minus 1 or plus minus 2. So this equation actually what tell about us that the wave vector kx is quantized in discrete steps of 2 pi by L. The mx is showing us the mode number. The same quantization applied to other dimensions such as y and z. So we'll be take L to the infinite, which follows kx. So the continuous value, we will be taking continuous value rather than being strictly to quantized. So the quantization of wave vector components, we will be seeing for y and z dimensions. So for in a cubic of side length L, the allowed wave vector in the y and z directions for the same quantization as the x. You can see here it was the same as x, but the z and y directions are given here. Okay, so now let to apply the periodic boundary conditions to ensure that wave function repeat identically after the translation by L. What it means that the wave function will be repeat itself even after we get the different L. So for example, we will be taking wave function at X and another for X plus L. So the total wave vector is then given by K is equals to 2 pi by L mx my mz, which will mx my mz are showing us the mode number of modes in X, in Y, in Z directions. So the magnitude of wave vector is related to frequency. So we can actually write it in a dispersion relation, which we have like written here in equation 2.62. K equals to omega k by c. So obviously the c is the speed of light and wk is the frequency oscillating for a wave vector k. So now the modes in a volume, we will be like seeing each integers of mx, my, and mz's corresponding to distinct mode of fields. So since the integers can be positive or negative, we are here taking the integer 2 as in multiplication, which actually show us the possibilities of positive and negative values. Okay. So the total number of modes within the small intervals are actually given by here. So the del m is totally actually given by 2 into L by 2 pi into cube. The cube is actually here taken because we have chosen the cubic cavity. So the forward del x and del y del z. Okay, kz. Okay. So approximating mode density of continuous space. So for the sufficient large cavity, we approximate the discrete mode count using the differential form. So we will be taking this dm as a more small, which will be written as a dm. So here we will be differentiating by cubic. So here we will be getting equation 2.64 as a v by 8 pi cube into dx into dky dz, where the V is equals to L cube, the volume of a cubic cavity. Now we express the wave vector in spherical coordinate. So the spherical coordinate in the wave vector was given as k equals to k sine theta cos phi, sine theta sine phi cos theta. So in spherical coordinate, the volume element is d kx, dky, dz. Okay, so we will be transforming into, so we can rewrite the above equation, this equation in this way, where the d omega is written as sine theta d theta into d phi. So we will be integrating it along the solid angle. So you can see here in solid angle element, d square dk arises from the Jacobian transformation from Cartesian to spherical coordinate, which we have written here, the k square dk, using the relation with a vector to the frequency, k vector omega k upon c. We write these terms in the frequency. So you can see here this above equation 2.66 is will be converted here 2.67. So the now we integrate over the solid angle. So the total number of mode in spherical shell between k to k plus dk, we integrate all over the solid angles. So it will be given as v k square upon pi square into dk equals to v rho k into dk, where rho k is written as k square upon pi square. So in the density state per unit volume in K space. So now we will be looking forward for the field quantization and the mode densities. So the mode density in terms of frequency represents the number of available modes per unit volume, which can actually given by this following equation. So rho k dk equals to d square upon pi square dk. So we will be now integrating it all over the solid angle. So the number of mode in range omega k. So now we are taking it in a frequency space rather than wave vector. So the omega k to omega k plus d omega k will be given as v omega square k upon pi square c cube d omega k. which rewriting using the mode density, as you can see here. So we just rewriting this following equation, which actually what it tells us. So actually it tells us the number of mode available increases proportional to the square of frequency in our cubic cavity. So now we will be explaining plane wave expansion for the vector potential. So we have taken that vector potential ART. So it can be represented as a superposition of a plane wave. Here we have written as this expression ART equals to summation of K and S, where S represents the independent polarization states, K is the wave vector, and EKS are real polarization vectors. So here we have taken the vector potential as a AKS into T e raised to IKR plus its complex conjugative. So now we will apply some orthogonality condition for polarization. So for the electromagnetic wave, the polarization vector EK1 and EK2 must be orthogonal, which actually satisfies this following equation or 2.73. So again from the Gauge condition, we can see here that K dot EKS equals to 0. The condition actually ensures that the polarization vector are perpendicular to wave vector, which is fundamentally requirement for the transverse wave. Okay, so the polarization vector from a right hand coordinate system will be given as k upon mod k equals to k vector. This ensures consistency in the definition of polarization directions. Okay, so the now we will be taking the continuous integral form of a mode sum. So in a free space, the summation over the discrete wave vector is replaced by integral. So we are taking here the summation of k all over v, which is volume upon pi square, and integrating all over k square up into dk. This replaces the summation by integral over the wave vector magnitude, making the field representation continuous in a k space. So now the harmonic oscillator represents all mode of amplitude. So the complex field amplitude such as KST follows the harmonic equation, which is the expression has given here. You can see here. Now which the general solution as will we know that AKS into T equals to AKS e raised to I omega k into T, where the initial condition is set as 0. So as the our amplitude increasing with time, it's starting from a 0. So the electric and magnetic field components using the Maxwell equation are the given below. As you can see here, the electric field is given in this expression or 2.78. And now from the magnetic field equals to E by C, we are just putting here the value of E and we are getting the magnetic field. This expression actually shows us the quantization of electromagnetic field, which was evolved in a space with the time. So now the further portion of a multimode will be explained by my group member, Saiket Ghosh. Thank you.
So now we use the path of quantization of electric field in the multimode domain. Now I have explaining this. In our classical theory of electromagnetism, we see that here we see the total energy H is equal to half of integration of over volume epsilon naught E plus 1 by mu B dot B. Now some boundary condition are applied, like integration of 0 to L in one direction, e to the power ikx dx is equal to L if kx is equal to 0, and 0 when kx not is equal to 0. Now if we apply in a 3D, three-dimensional, then we have introduced the k in x, kx, ky, and kz. So here is the equation where we use the delta function with the volume. Okay. Now the contribution of this energy field we have. So as we say, the Hamiltonian is equal to half of integration of over volume. This equation. If we
focus on the electric field only. Now, then we continue magnetic field. Here's some explanation of this. H is equal to half of integration of E dot E dV. Now, as we say earlier, that E is equal to summation of this equation. Okay. Now we can rewrite ERT is equal to this summation over this, and EKS is equal to this, where K is the propagation vector and S is the polarization vector. Then E dot E is equal to this summation over this equation, where different K values are applied. Okay. Now this is the equation. When we average out, when we isolate the term and average out, we have the term only K is equal to K dash and S is equal to S dash. As we apply this, the this equation is going on. And from this, we have this equation where R is equal to, R is the oscillator term, where R is equal to here. This is the equation. So total equation will be H is equal to this equation. And now when we summation over this, so H is equal to this, the final equation overall this. Now there is some term like AKs are the mode of amplitude, omega K is the frequency, mod of K by into C, and S denote the polarization as we say earlier. Now some vector identity are here. A cross B dot C cross D is equal to A dot C and B dot D minus A dot D into B dot C. So from this identity, we can prove this equation and this equation. Okay. As we explained the electric field, now we are going to magnetic field, and we have same identity from this. Okay. Now the total energy will be from that, the total energy. This is the total energy equation. This is the total energy equation. When we put this here, the value, we get this equation. Okay, equivalent to this equation. Now, in the path of quantization, so we have to go classical to quantization. We are introduce some quantities like AK is equal to 1 by 2 omega K epsilon naught B 1/2 omega K QKS plus I PKS. Okay, and A star is equal to this. So this is for the quantization. We have to quantize the electromagnetic wave in multimode. As we say, QKS is a generalized coordinate represent the real part of the magnetic field amplitude. And P is the conjugate momentum represent the imaginary part of the field amplitude. Those variables transfer the field into set of harmonic oscillator. Now, why we introduce this? This allows the quantization of the field using the same method of quantum harmonic oscillator. Okay, because we have deal with this oscillation, harmonic oscillation. So we have to quantize this same domain in this harmonic oscillator. That's why we introduce this. This lays the combination relation define the quantized mechanical behavior. So the fundamental communication relation in quantum mechanics, what happened? This become operator fundamental quantum communication relation. This shows that this operator, as we say earlier, that there is in a single mode. Okay, H is equal to this, and this single mode, as we say, like QKS, comma QKS is equal to 0, and PKS is equal to this. Commute, not this is commute, and this is not commute. Now we have to introduce the single mode method into this. So how can we convert Q to AKS? Okay, so this is our problem. This is the equation. AKS is equal to, as we know earlier from, and this one. So same commute relation is valid here also. So H is equal to this for single mode. Okay. So this is the number operator where n case is equal to A dagger A. Now, for simplicity, we can show that Ks and Ks is equal to Aj. Here we say this this thing Aks is equal to Aj and dagger, and number operator Aks is equal to Nj. So here's the Hamiltonian. So we deal with multimode. In previous case, we deal with single mode. That's why we have for multimode, we have number states, product of number state, cross product of number state. This is summation. And same thing, same validation is here. Hamiltonian operator, energy operator, operate on a number state, give the energy. This is the energy. And this is the orthogonality. Obviously, this will be valid because they are independent number state. And also annihilation and creation and annihilation operator also be introduced here. Same method and same like a n1 is equal to aj. This multimode equation is equal to root over nj. This. So we can introduce this nj as a zeroth operator, zeroth mode as like this, as we discuss in single mode operation. So from this equation, now we introduce AKS is equal to h cut 2 omega k epsilon naught v over 1 half AKS. So from that, from above equation, a cap r comma t, the vector potential, quantization of vector potential, this is the equation we get. Now, similarly, we have the electric field equation. Electric field equation. Similarly, we can introduce the similar electric field equation and also as well as the magnetic field equation. Here, k is equal to k cap is equal to k by mod of k. Then here's the annihilation operator when a case t is equal to a case 0 e to the power I minus I omega t. Same as the single mode case, the time independent annihilation operator free field is given by this. Okay. The electric field operator for intense can be written as like this, where ERT is equal to E plus E minus RT, where E plus is equal to this and E minus RT can be written dagger of E plus. Okay. Here we say that E plus is called as positive frequency part of field as contain all the term of oscillator. It's called the positive frequency part, and as well as E minus is going to negative frequency part. This form a essential collective annihilation operator, this rather than collect operator. Now talking about this is the total multimode equation of electric field, magnetic field and vector potential. Okay. So where we can use this? Okay, application of multimode quantum field. Like this is a now in nowadays this is a big area for researching, like in quantum quantum computing, quantum imaging, as I say, as my friend says, quantum cryptography, quantum sensing for meteorology, quantum communication, and laser technology. This is some major application. So this is our whole multimode discuss of multimode quantum field. So that's all from our side. Thank you. And then stop.